We now start chapter 3. In the first module, we will first define functions between vector spaces which are the spatial ones in the sense that they are not just functions but functions which preserve the linear structure, and that is why they are called linear transformations. Let V and W be vector spaces over a field F. A function t from V to W is called a linear transformation or a linear map from V to W over F if it satisfies two conditions. The first one, which is called additivity, that is t of x plus y is equal to tx plus ty for all x and y in V, and the second one, which is called homogeneity, that is t of Cx is equal to Ctx for all scalars C in F and vectors x in V. When T is a linear transformation from V to itself, that means when W is equal to V, then it is also called a linear operator on V, and when W is the base field F, that is T is a linear transformation from V to F, then it is called a linear functional on V. We know that the field F is a vector space over itself. Let us first talk about some basic properties of a linear transformation. Remember that the 0 in boldface denotes the vector 0 and not the scalar 0. So, the first property is t of 0 is 0, that means it sends the 0 vector of V to the 0 vector of W. Then the second property says that t of Cx plus dy is Ctx plus dty for all scalars C and D and for all vectors x and y in V. Third property says t of minus x is minus tx for all vectors x in V. And the fourth property says that t of summation aixi I equal to 1 to n is summation I equal to 1 to n ai txi. About the first property, we know that 0 plus 0 is 0 and therefore t of 0 is t of 0 plus 0. Now we use additivity of t, therefore it is t0 plus t0, and then if we cancel t0 from both sides, then we get t0 is equal to 0. And we have seen before that minus x, where x is a vector, is nothing but minus 1 multiplied by x. Here minus 1 denotes the scalar, and therefore t of minus x would be t of minus 1 times x, and now if we apply homogeneity of t, then it is minus 1 of tx and therefore minus tx. This proves 1 and 3, and 2 and 4 follows from the application of additivity and homogeneity of the linear map T. You can see property 4, this follows by induction on it. Let us talk about some examples. The first one is what is called the projection operator from R2 to R2, given by t of xy equal to x0. It is easy to verify that t is R linear, and this is in fact the projection onto the x axis. The next example is the rotation by an angle theta. we denote it by t theta, and this is a linear operator on the vector space R2 given by t theta of xy is equal to x cosine theta plus y sine theta. This is also our linear. The third example is the reflection operator t from R2 to R2 given by t of xy equal to x comma minus y. This is also our linear, and this is reflection with respect to the x coordinate. Some more examples. Consider the vector space of n cross n matrices over the field F, M and F, and define T to be T of A is equal to A transpose. Again, it is an easy verification that T is a linear operator on M and F over the field F. The next one talks about the differential operator. So, the vector space in this case is the collection of all polynomials with real coefficients in the variable x, Rx, and T from Rx to Rx is defined as T of Fx is equal to f dash x is the usual derivative of the polynomial f. The basic properties would tell you that T is a linear operator on Rx, and the next example is the integral operator on the vector space of continuous real valued functions on the closed and bounded interval AB. Is denoted by CAB, and T is defined as T of F is equal to integral a to b ft dt. This is also R linear, and first of all T of F is defined because every continuous function on a closed and bounded interval is Riemann integrable, and therefore one can define Tf, and it is indeed R linear. Now we define two very important subspaces associated to a linear transformation T. They are called the kernel or null space and the range. So, let V and W be vector spaces over a field F and T be a linear operator from V to W. The kernel of T is defined as the set of all those vectors x whose image is the 0 vector under T, and the range of T is collection of all Tx where x is running in V, which is the image of the map T. This is the theorem which says that kernel T is a subspace of V and range T is a subspace of W. So, how do we prove that? The first thing to note is that kernel of T is always non-empty, in fact contains the 0 vector. Why? Because T0 is always 0. Now, if we take any two vectors x and y in kernel T and the scalar alpha in F, then T of x plus y is T of x plus T of y. So, it is 0 plus 0 because x and y are in the kernel of T, and therefore, T of x plus y is also 0. This shows that x plus y belongs to kernel T, and T of alpha x is alpha Tx. This is by homogeneity of T, and that is alpha times 0, that is 0. Therefore, alpha x is also in kernel T. We have therefore proved that kernel T is a subspace of V. Again, the range of T, which is a subset of the vector space W, this is also non-empty because the 0 vector would surely lie there. And now to prove that range of T is a subspace of W, we start with two vectors x and y. Then x can be written as T of x1 and y can be written as T of y1 for some vectors x1, y1 in V. And therefore, x plus y can be written as T of x1 plus T of y1, which is T of x1 plus y1 by additivity of T. This shows that x plus y also belongs to range of T, and now if A is a scalar in the field F, then T of Ax1 is A of Tx1 and that is Ax. Therefore, Ax also belongs to range of T. Therefore, we have proved that range of T is a subspace of W. We have introduced linear transformations which are maps which preserve the linear structure. What is interesting about such maps is that there are two very special subspaces, namely the kernel and the range, which tell us a lot of information about linear transformations. So, our aim would be to understand these subspaces well. First, we would define dimensions of these subspaces. We would call them nullity and rank, and then we will prove a very important theorem which connects nullity, rank and the dimension of the domain vector space V, which is called the rank-nullity theorem. We define the concepts of nullity and rank of a linear transformation T. Nullity of T is the dimension of the subspace ker T or the kernel of T, and rank of T is the dimension of the subspace range T. If we assume that the vector spaces are finite dimensional, then of course rank and nullity are also finite numbers. Let us see some simple examples. Let T from V to V be the linear operator given by T of x equal to x for all x in V. This is called the identity operator, often denoted by I. So, we can see from the definition that kernel of I is nothing but singleton 0 vector and range of I is the whole vector space V. And therefore, in this case nullity of I is 0 and rank of I is dimension of V. And the next example talks about the 0 transformation, and we would be denoting it by 0 in boldface with an oval line, and the definition of the 0 transformation is T of x equal to 0 for all x in V. Then it is clear that the kernel of the 0 operator is the whole vector space V, and the range of the 0 operator is nothing but singleton 0. And therefore, the nullity of the 0 transformation is dimension of V and the rank of the 0 transformation is 0. Again, the example of the differential operator. So, V denotes the collection of all polynomials with real coefficients in the indeterminate x, the vector space Rx, and T from V to V is the linear operator T of fx equal to f dash x. Then kernel of T is the set of all polynomials f such that f dash x is 0, which would mean that those polynomials which are the constant polynomials, that means degree f is 0. Therefore, the nullity of T, which is the dimension of ker T, in this case it would be a finite number and it will be 1, but the range of T would be the whole vector space Rx, because it is not difficult to see that this linear operator T is onto V, and therefore the rank of this linear operator T would be the dimension of the vector space Rx over the real field R, and that is Aleph naught. Let us look at the example of the rotation operator, which we have already seen before. So, T theta of xy is given by x cosine theta minus y sin theta comma x sin theta plus y cosine theta. This is a linear operator from R2 to R2. Therefore, a vector xy belongs to kernel of T theta if and only if T theta of xy is 0. That means x cosine theta minus y sin theta should be 0 and x sin theta plus y cosine theta should be 0 simultaneously, which can be written in the matrix notation as the matrix cosine theta minus sin theta multiplied by xy is 0 0. Now, the matrix which represents the rotation operator, that is cosine theta in the principal diagonal and minus sin theta in the off diagonal positions. This is an invertible matrix with the inverse given by cosine theta in the principal diagonal and sin theta minus sin theta in off diagonal, and therefore kernel of T theta cannot be anything more than the singleton 0 0, and therefore nullity of T theta is 0. Now, if we take any x dash y dash in R2, then we can see that T theta of this vector x dash cosine theta plus y dash sin theta comma minus x dash sin theta plus y dash cosine theta is x dash y dash, and therefore the operator T theta is onto. Therefore, range of T theta is R2, which is a finite dimensional vector space over R, and it shows that rank of T theta is 2. Now, we come to a theorem. Let V and W be vector spaces over a field F, and let T from V to W be F linear. Suppose that V is finite dimensional and the set B, which is V1, V2, Vn, is a basis of V. Then the set T V1, T V2 and so on T Vn spans the subspace range of T. How do we prove this? So, first of all, T V1 and so on T Vn, they are definitely in the subspace range of T, and therefore the span of the set T V1 etc. up to T Vn is contained in the subspace range of T. Now, to prove the other way inclusion, let us start with a vector V. Then it can be written as a linear combination of V1, V2, Vn, because V1, V2, Vn forms a basis for the vector space V. So, V is equal to A1 V1 plus dot 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 An Vn for some scalars A1, A2, An in F, and therefore T of V is equal to A1 T V1 plus dot 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 An T Vn. This is because of the linearity of the map T. The expression on the right hand side of the equality is a linear combination of the vectors T V1 and so on up to T Vn, which belongs to the span of the set T V1 and so on up to T Vn. Therefore, range of T is contained in the span of T V1 and so on up to T Vn. Now, we characterize the one-oneness and the onto-ness of a linear transformation in terms of their kernel and range. So, the theorem says the following: let V and W be vector spaces over a field F and T from V to W be F linear, then T is 1 1 if and only if kernel of T is singleton 0 and T is onto if and only if range of T is W. Well, range of T is nothing but the image of T, and therefore onto property indeed follows from the fact that range of T is equal to W. So, the part 2 of the statement is clear. Now, we prove the part 1. Suppose that T is 1 to 1. We want to show that kernel of T is trivial. So, let x belong to kernel of T. Then T of x is 0, where x is a vector in V. But the 0 vector is definitely is equal to T of 0. Therefore, Tx is equal to T0. And by the 1 to 1 property of T, we can say that x must be the 0 vector. This shows that kernel of T cannot be anything more than the singleton 0 vector. Now, conversely, we assume that kernel of T is trivial and we prove that T is 1 to 1. So, let Tx be equal to Ty for xy in V. Then T of x minus y is 0. This is by linearity of T, and therefore x minus y belongs to kernel of T, and kernel of T being trivial, we get x minus y must be the 0 vector, that is x is equal to y. Therefore, T is 1 to 1. Now, we come to the rank nullity theorem. Let V and W be vector spaces over F, and let T from V to W be F linear. If V is finite dimensional, then nullity of T plus rank of T is equal to dimension of V. How to prove this statement? So, suppose that dimension of V is n. We know that kernel of T is a subspace of V, and therefore, dimension of kernel of T, which is the nullity of T, is also a finite number. Let us call it D, and D is definitely less than or equal to n. Let V1, V2, Vd be a basis for the subspace kernel of T. Kernel of T is a subspace of V, and V1, V2, Vd is a basis for kernel of T. We know that it can be extended to a basis of the whole vector space V. Let us name those extra elements as Vd plus 1, Vd plus 2 and so on Vn. Then this whole collection of vectors V1, V2 and so on up to Vn is a vector space basis for V. Now, we claim that the vectors T of Vd plus 1, T of Vd plus 2 and so on T of Vn would form a basis for the subspace range of T. If we can prove that, then we are done, because dimension of V is n, nullity of T is D. So, if we can show that rank of T is n minus D, then the rank nullity theorem is proved, and our claim says that T of Vd plus 1 and so on T of Vn would be a basis for the subspace range of T, and there are precisely n minus vectors in number. We note that V1, V2, Vd being a basis for the subspace kernel of T, T V1 and so on up to T Vd are all the 0 vectors, and we know that range of T is spanned by T V1 and so on T Vd and T of Vd plus 1 and so on T Vn. Therefore, range of T is indeed the span of the vectors T of Vd plus 1 and so on up to T of Vn. The only thing that remains to be shown is that the set T Vd plus 1 and so on up to T Vn is linearly independent over the field F. So, let us start with a linear combination of these vectors C1 T V D plus 1 and so on up to Cn T Vn is equal to the 0 vector, where C D plus 1 and so on up to Cn are elements in F. By linearity of T, we can write T of Cd plus 1, Vd plus 1 and so on Cn Vn is equal to 0. That is, the vector Cd plus 1, Vd plus 1 and so on Cn Vn belongs to kernel of T. But kernel of T is spanned by V1 to Vd, therefore, we can write Cd plus 1, Vd plus 1 and so on up to Cn Vn is equal to C1 V1 and so on up to Cd Vd for some scalar C1 up to Cd. But V1 V2 Vn is a basis for V, therefore, it is linearly independent, and that shows that the set T of Vd plus 1 and so on up to T of Vn is linearly independent. Therefore, we have completely proved the rank nullity theorem. Now, an immediate corollary to rank nullity theorem. Suppose that V and W are vector spaces over F of finite dimensions such that dimension of V is equal to dimension of W. If T from V to W is F linear, then the following statements are equivalent. T is 1 to 1, T is onto, and rank of T is equal to dimension of V. Well, the proof is a straightforward application of the rank nullity theorem, which says that nullity of T plus rank of T is equal to dimension of V. And the proof follows from the following observations. T is 1 to 1 if and only if kernel of T is trivial, if and only if nullity of T is 0. So, if nullity of T is 0, then rank of T is equal to dimension of V. But we know that rank of T is dimension of V if and only if range of T is equal to V, if and only if T is onto. And therefore, we have proved that 1, 2 and 3 are equivalent statements. We have introduced the notions of rank and nullity of a linear transformation T, and these are extremely important when we try to understand a linear transformation. We have seen the rank nullity theorem, which creates the relation between these two numbers and the dimension of the vector space, and the last corollary to rank nullity theorem, which was proved, which says that if we have a linear operator T from V to V, say, and if V is finite dimensional, then the one-oneness and the onto-ness of the linear operator are equivalent. This is something very special, which obviously does not happen for a map between sets.